everyone, so glad you could join us today, grade 12s, and it is obviously the first lesson for the new term, so I hope that you're all excited and ready to get on with term 3 so that we get closer to final exam preparation times. Okay, I know it's scary, but we are already into the third term. So we're going to start today's lesson with, well, through the whole lesson, not just starting the lesson, but we're going to start the lessons this term by looking at similar triangles. And you guys will remember similar triangles because it is something that you did in grade 9 and grade 10 as well, where you had to prove triangles were similar. All right, so we're going to now build on that knowledge and extend that knowledge. But I first want to start just reminding you what it is that we are talking about when we talk about things like proportion and ratio and how to find similar triangles. All right, so these are terms you are familiar with, but maybe you don't quite understand them. So this is going to clear up any confusion you might have. Let's have a look. All right, so remember the word proportion. Now, proportion actually gives you no indication of the actual length, guys. It doesn't tell you what the length is. It only indicates what the ratio is between different lengths, all right? Remember, to prove triangles are similar, there were two ways that you've really looked at so far. That's by showing that the two angles were equal. So we'd use the property that all the angles were equal, and we called that angle, angle, angle. Or we showed that the three sides were in proportion, and we've used here side, 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 but it's not really a reason that you would often put down with similar triangles. You would just say that the sides are in proportion by showing which ratios are equal. Also important when we're talking about geometry, theorems are definitely examinable. So you need to know them. They can be asked in your final exams, all right, and certainly in your prelims as well. It is very important when you're dealing with similar triangles to correctly order the letters. It's extremely important, as this will indicate which angles are equal, so which corresponding angles are equal, and which sides have the same proportion. So you need to label your triangles correctly when you state your similarity. You may also be asked to prove similarity among triangles that are found within circles. So now when we're talking about circles, remember all those theorems you learned in grade 11, your circle geometry. You need to know all of those theorems because sometimes you need some of those properties to be able to prove that triangles are similar. You need some of those properties from the circle theorems as well. You need to remember all of the stuff, obviously, that you've done so far in geometry to be able to be very successful at grade 12 geometry. Now, before we start talking about similarity, I'd like to remind you about some of the theorems you've learned before. So we're going to go back to grade 10 here and remind ourselves about things like the midpoint theorem and the proportion theorem and that kind of thing that you have learned before, and maybe don't realize or quite realize that this can also be examined within your similar triangles. It can be examined, but indirectly, but you will draw on this knowledge that you already have, and often in your statements and your reasons when you're setting out your geometry proof, your reason may well be a theorem that you learned from grade 10. Okay, so let's look at the midpoint theorem, which you learned in grade 10. The midpoint theorem tells us that the line joining the midpoints of two sides of a triangle. All right, so you have a diagram there where you can see the line joining the two sides of a triangle. So line BC is parallel to the third side and equal to half the length of the third side. Remember this, the midpoint theorem? So you've got a line BC that joins the midpoint of AD to the midpoint of AE. All right, that line BC will be parallel to DE, and it would also be equal to a half DE. So a half the length of DE. And the converse of this theorem tells us that a line that's drawn through the midpoint of one side of a triangle and is parallel to the second side bisects the third side. So in other words, if I've got that D is the midpoint of AB, and I know that DE is parallel to BC, then by the converse of the midpoint theorem, I can conclude that AE will be equal to EC. In other words, E is the midpoint of AC. Why is this important? Why is it important to remember the midpoint theorem? It does come up where you have triangles with parallel lines in them, and it often you've got to then draw on that knowledge to work out the ratios that they're asking you to prove in certain questions. All right, so it is important to remember. We talked about ratio, but what is a ratio? Okay, a ratio really describes the relationship between any two quantities which have the same units. Okay, it's got to be in the same units. So for example, we would use ratios to compare weights. Okay, so she weighs 80, I weigh 40, whatever the case is. You can also compare heights, or you can say, well, he's 2 times as tall as the other person. We also use ratios to compare lengths, currencies, and the list goes on. So what is a ratio again? It is a comparison between two quantities of the same kind, and the ratio itself has no units. So for example, if I'm saying, well, she is twice my weight, that's twice or 2 times. There's no kilos attached to it. It's just a reference. Okay, so your ratio itself has no units attached to it. Okay, so for example, if the length of a rectangle is 20 centimeters and the width is 60 centimeters, okay, so let's just draw up a quick rectangle, not that we need it, but let's put it in anyway. Okay, so we've got a rectangle like this. We know that the length is 20 and the width is 60, okay? We can then express the ratio between the length and the width of the rectangle as a third. So I'm saying the length we know is 20 and the width is 60. So that can be simplified to the ratio 1:3 or 1/3. So another way to say 1/3 is 1:3. Okay, to represent the ratio between length and width. And what's important is your order. So if I'm taking the ratio of length to width, it's going to be 1:3. However, if I wanted to go the other way around, and I want to go width over length, or width is to length, that ratio is going to be 3/1 or 3:1. So the order in which you state your ratio is important. So this ratio of length to width being 1/3 describes the length of the rectangle relative to its width. It doesn't tell us, guys, it doesn't tell us that this is 1 centimeter and this is 3 centimeters. No, it tells you the ratio of the two relative to each other. As you can see, the actual measurements were different to your ratios. So please do not confuse ratios with actual lengths. A ratio is written often as a fraction, or as I showed you, it can be written in an alternative form. It's always or usually given in its simplest form. It does not indicate actual length, as I just said to you. Now, sometimes you may think it's a good idea to convert a ratio because it's a fraction, like 1/3. Well, I know the equivalent form of 1/3 is 0,3 recurring. Please don't do that, okay? You need to be completely accurate in stating your ratio as a fraction. Don't start rounding off and writing recurring decimals and that kind of thing, okay? So you will leave your ratio as a fraction. Don't convert it to a decimal. Now, if two ratios, as we've seen before, two ratios can be equal to each other, right? Then we say that they are in the same proportion. So you often see these terms used interchangeably, proportion, ratio. What does it mean? Well, proportionality is really describing the equality of the ratios. So for example, you might have something like AB over BC is equal to CD over DE. Just say, okay? So AB over BC will be a ratio, but when we describe the equivalence, so we're saying AB over BC is equal to CD over DE, what we're talking about there is that they're in the same proportion. So proportionality describes the equality of the two ratios. Talking about proportion, remember the proportion theorem. And that tells us that if a line is very similar to the midpoint theorem, and in fact, the midpoint theorem can be proved from the proportion theorem, it tells us that if a line is parallel to one side of a triangle and it intersects the other two sides of the triangle, then the line divides these two sides proportionally. All right, so you've got a line DE being parallel to BC, and as you can see, it's intersecting two lines of the triangle. It will then divide the two sides proportionately. So in other words, AD over AB will be equal to AE over AC, or any variation thereof. Okay, the converse of that theorem tells us that a line which cuts two sides of a triangle proportionately will be parallel to the third side. So just say you didn't know that DE was parallel to BC, but you knew that AE over AC was equal to AD over AB, you will then be able to deduce that DE is parallel to BC, and that's just by using the converse of the proportion theorem. So really what we've started doing is just reminding you of things that you have done in previous grades and that you have looked at already. We haven't really started talking about similarity, but what you see is the importance of the terminology that you've used so far. You now hopefully understand what a ratio is and what a proportion is, all right? And now I really want to start talking about similar triangles, okay? You have done this before. You've seen this in grade 9 and grade 10, but just a reminder. The symbol for congruency, remember congruency means two things are identical, is those three horizontal lines. The symbol for similarity is as you see on your screen, so three upright lines. All right, be careful to label similar triangles correctly. So the order in which you state your similarity of triangles is very important. Okay, now when we're talking about congruency, similarity, some learners confuse congruency with similarity. Remember that congruency means the two objects or items or shapes are identical, whereas similarity means that they have a similar shape. The only difference is their size. So you can resize the one and maybe turn it around or flip it around to get the other one. So the only difference in similar shapes is their size. Okay. You've seen that to prove triangles are similar, we need to either show that two angles are equal, because obviously if two angles are equal, then the third angle automatically by sum of angles in a triangle would be equal to each other, or you can show that the three sides are in proportion. So for example, for angle, 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 if I've got triangle ABC and I know that angle A is equal to angle D and angle B is equal to angle E, then automatically angle C here would be equal to angle F because of sum of angles of a triangle. So therefore we would state those two are similar and our reason would be angle, angle, angle. If you were given the length of the sides, then you could make claims about the ratios, and if you got that MN over RS, okay, so the one side of the triangle over the other side is equal to the same ratio as one side of the first triangle over the one side of the second triangle, and then obviously the last pair also being equal, then if those ratios are all equal, you can say that those two triangles are similar for your reason sides are in proportion. Now there's one more way, and we don't really discuss this much. It's not really so much of a proof in that, so we're not going to dwell on it too much, but there is one more way that you can show that two triangles are similar. And that is if you've got a pair of sides that are in proportion and you've also got that there's an angle between them that are equal, then those triangles will also be similar. Okay, so if you look at your screen, I'll just demonstrate what we're talking about there. So if you've got two triangles, ABC and XYZ there, And if those two triangles have two pairs of sides in the same ratio, okay, so those are the sides if you can't see them clearly on your screen. So if in these two triangles, they have a pair of sides that are in the same ratio and the included angles, so the one between the proportionate sides, are also equal to each other, then you can also conclude that those two triangles are similar. But as I say, it's one that you don't see much, but it is something that you need to bear in mind. Okay, so I've given you all the theory necessary and that you need to be successful at similarity and geometry, but it all comes down to how you apply that knowledge, right? So we need to look at questions on how we apply all the theorems that deal with triangles, and then maybe even some of the theorems that deal with circles. So what we're going to do is, while you revise, refresh your memories about what similar triangles are, we're going to take a quick break, and then when we come back, we'll have a look at applying what we know about similar triangles. Welcome back, everyone. So a reminder, in today's lesson, we're looking at similarity. We're looking at the similarity of triangles, and we've already seen the ways that you can prove that triangles are similar. The most common ways that you guys are aware of is by proving that two angles are equal in each of the triangles, or showing that the sides are in proportion. So using that knowledge and all the other stuff I've shown you as well, let's get into our first question for today. And really what I'd like you to do here, guys, is to take down the diagram and mark off as much information as you can and possibly attempt the first one. I'm going to give you 3 minutes to have a look at this. Okay, everyone, I'm not sure how much of this question you got through, but hopefully you were able to at least get the first part down where you had to prove that the two triangles were similar, and we'll go through the whole thing, of course, together if you missed any part of it, okay? So you were given two triangles and you were told, your only bit of information was that AB was parallel to DE. The first question asked you to prove that the two triangles formed by those intersecting lines, ABC and EDC, were similar. Okay, now since you haven't been given any information about the lengths of the sides as yet, the only way you can prove these two are similar is by using your angles. Okay, so I've got ABC and EDC. I'm going to look for equal angles. And all I need is just one pair to be equal, really. All right, so for example, I know that because these lines are parallel, angle A would be equal to angle E. Okay, so that's one set. And then the other one that we've got two that we could see quite easily, but using the parallel lines, angle B is equal to angle D because those are alternate angles. If those two angles, those pairs of angles are equal, then obviously the last two are going to be equal to each other because they are the remaining angles in the triangle, or certainly, as you can see, they are vertically opposite. Okay, so let's set up our proof. So we start by saying, in triangle ABC and triangle EDC, we know the following things. Firstly, we know that angle A is equal to angle E. And the reason for that is they are alternate angles, and they had already told you that AB was parallel to DE. Okay, in a similar way, we know that angle B is equal to angle D, also because of alternate angles. And our reason there is the same, it's alternate angles, and AB is parallel to DE. Your last angle is automatically equal because it's the remaining angle, but if you want to state its name, it's ACB. Angle ACB is equal to angle DCE. And the reason for that is vertically opposite, or you can just say remaining angle. Okay, therefore we can say that triangle ABC is similar, and this is where you need to be careful now. If you're going to state triangle ABC, okay, you need to use the same formation in the other triangle. So you need to start with the angle that was equal to angle A. So we need to start with side E, so vertex E. So we're going to start with E, and then we go to B in the bigger triangle. So here we need to go to D. So it's going to be triangle EDC, and that's by naming the vertices of the triangle correctly, right? So therefore, those two triangles are similar, and the reason is angle, angle, angle. Okay, now remember, when you get two triangles being similar, the other thing that it gives you information about is the ratios between the two triangles. So we can write all those ratios down, but it might not be necessary for the next question. So let's read what the next question actually requires of us. So here it tells us that side AC over AE is equal to 5/7. Okay, so let's see where that is. AC over AE is equal to 5/7. And then we look at that and we think, but hang on, AE is not a side in our triangles that we've just proved to be similar. So now what do? All right, well, they carry on to say that AB is equal to 4 centimeters, and then they would like you to find the length of DE correct to one decimal place. So let's go back to this discussion. We know what the length of that the ratio AC to AE is 5/7. We don't know what the actual lengths are. Remember that. The only length that we've been given is AB. So AB we're happy with because that's a length in one of the triangles that we've proved similar. But what about AE? How do we deal with that, and how does it help us now to then work out the length of DE? Well, guys, because you've been given the ratio of the sides, you've got AC over AE. What I'm going to show you to do is let X be a placeholder for the actual value of the length. So when I've been given that AC over AE is 5/7, yes, I can put the ratios in, but I know that AC is going to be 5 times X, whatever the length X is, all right? And AE is going to be 7 times X, whatever X is, obviously being the same quantity. So by using this placeholder X, hopefully you guys will be able to see more clearly that 5 and 7 are not actual lengths. They're just the ratios. But what it does tell me is if the whole length AE is 7 times some number X, and the length AC is 5X, then CE must be 2X, because CE is equal to AE minus AC. I want to get to some value that can represent CE, because that is a length in the triangles which I've just proved similar. Okay, and that could potentially help me to work out the side DE. Okay, so let's set this up. So following from the similarity, we know that there are certain ratios that are in proportion, so that are equal to each other. So we know, for example, remember you've been given the length AB and we're looking for DE. So we've been given AB, we're looking for that. Okay, they've also given us information about AC in relation to another length, and we've seen what we could work out EC as well in terms of X. So therefore, using my similar triangles, I can state the following. AB, length AB over ED. So do you see what I'm doing? I'm going from the same, this is why the vertices are so important. I was going in the triangles using the correct vertices that were proved in your similar triangle. So using my vertices, I can state now that length or side AB over ED will give me the same ratio as AC, which is the two outer ones, over EC. Okay, so going back to your diagram, this is what we're saying. We're saying AB over DE is going to be equal to AC over CE. And that is true. That comes straight from our similarity. We don't have to set up a proof for this. And this is since triangle ABC is similar to triangle EDC. Remember, you were given that AB has a length of 4 units and DE is the one you're looking for. Now, AC is to EC. We don't have the actual values, but we do have the ratios. So AC to EC is going to be 5x over 2x, or the ratio 5/2. So I'm going to just leave it as with the x's in place, because as you will see, the x's will cancel out to just give me my ratio 5/2. Okay, the reason I use the x's was so that you guys don't confuse actual length with ratio. Okay, now we can cross multiply and we'll get that 8 is equal to 5 times ED. This is the same as finding an LCD if you haven't come across cross multiplying before. And then we divide both sides by 5. So we get that ED is equal to 8/5. They're set to one decimal place, so you simply use your calculator and divide 8 divided by 5, and we get 1,6 centimeters. So therefore, ED is 1,6 centimeters. right. Okay, guys, so here the key thing that you would have taken out of this is how you can use your similar triangles to help you calculate the lengths of sides in your triangle. So to help you find the unknown values. So if you know the two triangles are similar, you can draw on all those equal proportions to help you work out unknown lengths. Okay, I think it's time for us to take a quick break while you think about this, and when we come back, we'll do another question on similarity. Back after this. Welcome back, guys. So a reminder that today we're looking at similar triangles, and so far we've seen how similarity can help us to find the lengths of unknown sides in our triangles that are similar. Okay, so continuing with the idea of similarity, I'd like you to have a look at another question where you've got to prove similarity and then also use the fact that the sides between the triangles are in proportion to deduce other things. Okay, so I'm going to give you 3 minutes to take this question down. It is quite a long one. Take down the diagram most importantly, and then take down the questions so that you see what it is we're going to be doing in each part of this question. Your 3 minutes starts now. Okay, everyone, so I want to get straight into this question because there's quite a lot that we've got to get through. You just follow along with me, and hopefully a lot of you got to the same conclusions as well. Okay, you were told that in circle O, RP is perpendicular to PQ. It's circle O, so we know that O must be the center, and we've got RP perpendicular to PQ, so that means that angle P is equal to 90 degrees. You were also told on the diagram that line QS is equal to SR. Okay, so I already start making some conclusions. I know from the converse of the line from the center of the circle, if that line is drawn to the midpoint of that chord QR, that means that angle S must be 90 degrees, and that's really just the converse of the line from center theorem. Okay, they said prove that triangle PRQ, which is the big one, all right, the big triangle PRQ, prove that that is similar to triangle SRO. So let's get that one in a different color. So that's that little one there. So immediately I see, well, I don't really know anything about lengths as yet, so I'm going to go for angles. And I can see that angle R is common, so let's set this proof up. So this is A, and we say in triangle PRQ, and triangle SRO, we know the following things. Well, we know we were given that angle P is 90 because RP is perpendicular to. So angle P is 90, and we were given that RP is perpendicular to PQ. Okay, so that was really given to you. We need another angle that's equal to 90 degrees for this proof to work, and we have it in the fact that angle S is equal to 90, and that's because it's the converse of our line from center theorem. Since QS is equal to SR and O is the center of the circle, it means that angle S must be 90 degrees. And this is what I started off today's lesson telling you, is you need that information about circle geometry sometimes to prove similar triangles. All right, so angle S is equal to 90, and that's because QS is equal to SR. Okay, so therefore we've got angle P is equal to angle S. Another thing that we have is we have angle R is common between the two triangles. It's a common point. Okay, so therefore the last angle is equal to each other because it's remaining angle. So we're going to go straight into and say therefore triangle PRQ is similar to, and we get the order right here. So if I'm going triangle P from the 90 to the common angle to the other angle, then I need to follow the same pattern in my little triangle. So I go from angle S to angle R to angle O. So it's triangle SRO. So those two are similar, and the reason being there, angle, angle, angle. Okay. Now that we've got that proof set up for our similarity, obviously we know that certain ratios are going to be equivalent. So those sides are going to be in proportion. So they say to you, prove that OR over side SR is equal to QR over PR. So really this is a deduction from your similarity, but not many learners realize that you can go within the triangle pairs, and that will be equivalent to a ratio to the other triangles. Okay, so what I'm saying is if you have two sides in a triangle, you can write them as a ratio over each other, and that will be equivalent to another ratio between two sides in the other triangle. All right, so this is what we're saying here. We know certainly from our similarity that pairs of sides between the triangles, so for example, PR over SR will be equal to RQ over RO. However, you can also go that PR over RQ will be equal to SR over RO, and that's really what they're asking you to show here, so we can't use that fact. Okay, so we asked here to prove that OR over SR is equal to QR over PR. So we know from the similarity, we can say that side PR over SR will be equal to side RQ over RO will be equal to, which is the one that we've left out, so we've done RQ and we need PQ and SO. And this comes straight from your similar triangle. So it's since triangle PRQ is similar to triangle SRO. Okay, so I can make that conclusion. But they want a different version of these ratios. They want the sides between the triangles. So in other words, they want OR, which is those two there. Let's use a different color. The last two vertices in your second triangle over SR. So it's the first two vertices. And then they've got QR, which is the same obviously as RQ because multiplication is commutative, over PR. So that is another deduction that follows straight from your similarity, but if you didn't know that, you can prove it by using these two. Okay, those have all the same vertices in place and the same sides. All right. So going from that, I can say cross multiplying, I will get that PR times RO, remember, is the same as OR, so I'm going to write it as OR, is equal to RQ is the same as QR, so I'm going to write it as QR times SR. Okay, so have a look at what we've done. We've just cross-multiplied the two ratios on either side. Okay, it's the same as finding an LCD. Now I want to have OR over SR. So what I need to do is I need to divide both sides by SR, and then I want QR over PR. So I need to divide both sides by PR as well. So we're going to divide both sides by SR and PR. When you do that, you end up with OR over SR is equal to QR over PR, which is what they asked you to show. Okay, so really now, as I was saying to you, it is a deduction also from your similarity where you can use the vertices from each triangle and you can say that they are in the same proportion as the same vertices that fall in the same place in the other triangle. All right, but you see that you can actually show it and prove it as well. Okay, all right, so now that we've got that information, let's have a look at part C. Here they give you more information. They say now that SR is equal to 18 millimeters. So SR is 18. Obviously that means that QS must be 18 because QS was equal to SR. So we've got the whole length, QR. QP is equal to 20. And they would like you to find the radius of the circle correct to one decimal place. So your radius, if we're going from the center of the circle and following through, our radius is going to be the length OR or the length OQ. Okay, in this case, it seems like it's going to be easier to get to OR using the ratio that we've just proved just now. Okay, being in proportion to another one. So really what we're looking for is OR. Okay, I can see that I've got a 90-degree triangle. So that means straight away when I start thinking about proving things, I need to see, okay, well, what can that help me with? That's going to help me with Pythagoras. In triangle PQR, I could work out the length of PR. And we are going to need that. So let's quickly write that down. We're going to say that QP squared plus PR squared is going to be equal to QR squared, and the reason for that is Pythagoras. Put in the values that you've got, so we're going to have 20 squared plus 36, so PR, that's the one we're looking for, so PR squared is equal to QR, which is 36, 18 plus 18 squared. So therefore PR squared will be the hypotenuse squared minus the shorter side, and then take the square root of that to find PR. So it's the square root of 36 squared minus 20 squared. If you do that on your calculators, you're going to end up with the square root of 896, and that you can simplify down to 8 root 14. We're just going to leave it like that form for now. We're not going to round that off as yet because we haven't found what it is we're looking for, because remember, you asked to find the radius of the circle. You aren't asked for PR, so don't round off just as yet. Okay. Now we're going to use the ratio that we've just shown, okay? And the ratio we've just shown, having equivalence, is that OR over SR was equal to QR over PR, okay? So we've just shown that. So we can say, well, we know, so this is part C, I know that OR over SR is equal to QR over PR, because we just proved it in B. Okay, so therefore putting some values in, we know what PR is. Remember, we've just worked it out, right? We've got it as 8 root 14. What were we looking for? We're looking for the length QR. Okay, so if we go back to my little writing up here, there we go. So if we go back to this little red segment here, we know what PR is. We're looking for OR. Do we have QR and do we have SR? Well, we know what SR is. It's 18. QR, if you go back upwards, QR was the sum of QS plus SR, so we have that length as well, is 36. So we're going to put that all in now to work out OR. So I'm going to say OR over 18 is going to be equal to QR, which is 36, over PR, which was 8 times the root of 14. We're then going to multiply the 18 out because we don't want a denominator, we just want OR by itself, so timesing both sides by 18, I'll get that OR is equal to 18 times 36 over the square root of 14 times 8. And when you put that entire thing into your calculator, you should come out with 21,6 millimeters. Okay, you can just double check that on your calculator as well. And therefore, we've got that the length of the radius, which is OR, is 21,6 millimeters. All right, guys. Okay, so we are running out of time, but we managed to get all of that in. Hopefully, you followed along with me and you understand how we can use the similar triangles to prove that ratios are in proportion, and that you've seen how we can use our similar triangles to calculate unknown values. And that's really what the kind of thing you be examined on, is using that similarity. So yes, you might be able to prove it, but can you use it? That's the important thing. All right, so keep practicing that. Until next time, cheers.